Welcome once again. I'm Liam Kennedy, your host for tonight's episode of Look Up Tonight. This is the cable show of the Orange County Astronomers, and we're one of the largest amateur astronomy clubs in the country, and invite everyone to watch our show and to learn what our club is all about and how you can learn about this wonderful hobby.
Simply a clock with a single moving part, and that part, of course, is the sun. There are two objectives for sundials, ornamentation and function. But a sundial is more than just a garden ornament. A properly designed sundial can be read and will be accurate to less than a minute. And in fact, really well installed sundials that are carefully constructed can be read to 15 seconds. Let's look first at some typical sundial features. Now, these are features of what you would normally see as a garden sundial or a horizontal sundial. So there's a horizontal plate, and it is truly and important that it be horizontal. It has the hour line scribed around it, and it has a gnomon. Now, the interesting thing about the gnomon is that this angle right here is equal to the latitude of the location of the sundial, and that actually turns out to be very important. And I'll also call your attention to the fact that the position of the sun for a given hour of the day changes seasonally. And of course, that's a correction that must be introduced in sundialing. Sundials are also calendars, and Stonehenge, which of course is a very well-known monument, is in fact a calendrical sundial. Now, Stonehenge dates from the period of about 1900 to about 1650 BCE. That was the period of construction. But in fact, it is a sundial, and there are numerous alignments, and if you look through the columns at Stonehenge, you can actually find the rising sun at sunrise for the equinoxes. The other interesting thing about Stonehenge are these 56 little holes that are around the perimeter of Stonehenge. Those are called Aubrey holes. Gerald Hawkins studied Stonehenge with a computer, first in the early 1960s. And he found a periodicity in lunar eclipses that's 56 years. No one had seen that periodicity before he studied it with a computer. The reason he studied it is because there are, in fact, 56 Aubrey holes around Stonehenge. And he was looking for an association about why there might be 56 Aubrey holes. Another early sundial is Egyptian. This dates from about 1500 BCE. This dial is used by casting, it's positioned away from the sun. The sun would be down in this direction, and this style, this would be the gnomon, and this edge would be the style that casts the shadow, and it would cast a shadow along this surface here. So this style is one that would be positioned or repositioned during the day by the user. There's been some very recent archaeology finds regarding this particular sundial, and there was just a German archaeological paper published that would indicate that there's a lot more sophistication and math in the design of this sundial than anyone has believed before. So it'll be interesting to find that if that archaeological paper stands the test of time in other people's review. Yet another early sundial is the hemicycleum. This dates from the 1st century to the 2nd century AD, and it's a stone dial. It's hemispherical on this surface. The hour lines are inscribed on the hemisphere, and the shadow is cast by a rod that would normally be here, but of course is missing at this age, but it's drawn over here in this picture. So as the sun moves through this arc up here, the gnomon, this horizontal rod, casts a shadow down on this surface. Other early sundials are called mass or scratch dials, and these date from the Middle Ages, 12th through the 15th century. They would normally have had, these would be vertical dials, they would normally have a gnomon in the center that would be a horizontal stick protruding from that hole. And again, you can see that there are numerous attempts at scribing hour lines on here. One of the early purposes of dials, of this form of dial, was to identify the times for prayer. So you often found these dials associated with churches. This is an altitude dial, or it's also called a cylinder or shepherd's dial. Here's one that dates from 1550 and it was made in Germany. The dial works by expanding this gnomon here, and the shadow is cast from the sun down on this surface here. And the hour lines are scribed along with these arcs. So you rotate the dial to set the calendar date that you're using, and then you can read the time by the tip of the shadow on this altitude dial. Well, we need to talk a little bit about time and hours. First, there were times identified by the tides. So the Saxons had times that they identified by the tides, and they were called, for example, evening tide. There were canonical hours. These were medieval and the times when people were called to prayer. Temporal or seasonal hours, these are 12 hours counted from sunset or sunrise, and the daylight hours are longer in summer than in winter. So these hours are not constant hours. And then finally, equal or modern hours. These are 12 equal hours counted from midnight or from midday. The significant change occurred between the temporal hours and equal or modern hours. What I choose to call scientific sundials are sundials that now have a gnomon, that would be this device here, whose style is pointed at the celestial North Pole. Prior to the discovery that sundials just worked better and were more accurate if you align the edge of the style with the celestial North Pole, dials were not very accurate. But with the introduction of this idea where you can actually align the sundial to the celestial North Pole, and this gnomon angle down here is equal to the local latitude, that's when dials really became scientific and became accurate. And over here is an example of a multi-faced, a polyhedral dial. Each one of these devices is in fact a gnomon for this particular face. And this dates again from the 17th century. The interesting thing about this is, of course, that the gnomons here point all up at the celestial North Pole. There are many types of sundials. The common types, and the most common type, is a horizontal. If you see a sundial in a garden, it will most likely be a horizontal sundial. That's identified by having its dial placed horizontal. It's typically on a pedestal and seen in a garden. Vertical dials, the dial plate is vertical, and it's often found on the walls of churches and sometimes modern buildings. An equatorial dial has the dial plate set in the plane of the Earth's equator. And I'll show you some examples of each of these dials here shortly. Polar dial has the dial running east-west and parallel to the Earth's axis. And a polar dial is defined as having a planar dial face. That is, the dial face is flat. There are many kinds of portable dials. I have a reproduction of an early 1500s dial on the display table that you're welcome to come and take a look at the break. And then finally, the remaining common type is an analemmatic dial. You often see these dials in elementary schools because they're very easy to construct. In this case, the vertical gnomon is the person's body. And typically there are date lines scribed on the face of this dial, and you walk and stand on the marker corresponding to the current date. And then the shadow from the tip of your head falls on marks that indicate the time. And of course, these dials are approximated because the height of the individual is important, so they're typically designed for the age of the student for the school where they're constructed. This is an equatorial trigon model of a sundial. This actually is a graphic that shows all the different kinds of sundials that I talked about previously. So let me point them out to you. First of all, here is a horizontal dial, and this would be the dial face for horizontal. And again, this is the gnomon, and it points at true celestial north. Here is an equatorial dial, and the plane of this dial face lies in the plane of the equator, here. Here is a polar dial face, that's this one sitting at an angle down here. That dial surface is actually pointing at true celestial north. It runs due east and west, and it's flat. Finally, here is a vertical dial, and there are two versions of this. There's one on this side with the gnomon pointing down. That would be on a south-facing wall. And there's one on this side with the gnomon pointing up, and that would be on a north-facing wall. Now, this is a computer-generated graphic, but there's also a solid physical model of this dial, and again, this shows much the same thing. You've got the horizontal dial down here. Here is the polar dial face. Here is an equatorial dial face. Here is a south-facing vertical wall sundial. And on the other side here is a north-facing vertical sundial, again with the gnomon always pointing up to celestial north. Nicholas Kratzer was the keeper of the king's orologs. That's King Henry VIII. And this painting shows a number of, on this table here, shows a number of devices that he developed. And in fact, there's a cylinder or altitude dial, and here's another polyhedron dial. Kratzer's dial that he built for Cardinal Wolsey is now in the Oxford Museum. It's a polyhedral dial. Each one of these faces has a different function and is in fact an independent sundial. And again, these are all scientific dials. That is, if you look at these gnomons, you'll find that they're all pointing up to celestial north. How do we best know, or most of us know, William Outred? Well, it isn't from sundials. It's because Outred developed what? Anybody know? Slide rules. Okay. But he also did sundials, and in fact, he designed this double dial, which had two gnomons. It had an analytic dial and a horizontal dial, and this is the actual dial that he developed. Elias Allen is best known as the father of the English scientific instrument industry. That was the era when precision was introduced into the production of these scientific instruments. And in fact, this is a pocket dial, and this is the one for which I have a very nearly exact reproduction for you to see. Well, sundials don't tell clock time, and that's important to understand and to apply the various corrections for. Why do they not typically tell clock time? Well, there are two major reasons. The first reason, of course, is the equation of time. That was first developed and defined by John Flamsteed in about 1672. The equation of time has two major causes. The first is that the Earth's orbit is elliptical rather than circular, and the fact that the Earth's axis is tipped, that 23.5 degrees that's so important to causing our seasons. I've given this presentation a number of times to different kinds of groups, and I'm always astonished, and I don't expect to be here tonight, but I'm always astonished at the number of people who don't really understand why we have seasons. That is, the fact that the Earth's rotation axis is inclined and the position of the sun changes during the year. So if you look at this path here, which would be the summer solstice path, and you take 10 a.m. and you maintain that 10 a.m. throughout the seasons. Here would be the equinox path, and here would be the winter solstice path. Well, for a given time of day, the sun is in three different positions, and therefore if you had a gnomon, this just happens to be a vertical gnomon, but any kind of gnomon, it would in fact cast three different shadows. That would show three different times. So this is the embodied by the equation of time correction. Sometimes it's hard to convince people that the sun really moves. There's been a number of these pictures taken through the years. Until very recently, there were only 7 known successful pictures. Denis DeSico did one. He's very famous for that. These pictures are taken in Greece, and this author or photographer was generous enough to send me a high-resolution photo and release to use this picture. This is actually a multiple exposure picture taken throughout the year of 2003. And there are 45 individual exposures that show the position of the sun. So the picture was taken with a solar filter, and then finally one picture was taken to show what the foreground image is. But the important thing here is to appreciate that this 23.5 degree tilt, as the Earth follows its orbit around the sun, causes this positional change in the sun, and we recognize that as an analemma. There are two contributors to the equation of time as I described, the fact that the orbit of the Earth is elliptical and the fact that it's tilted. So this is the effect from the elliptical orbit. This is the effect from the tilt of the axis, but they add together. So if you add those two effects algebraically, you get this effect, and this is in fact the way the equation of time is often represented. Dates on this axis and time corrections along this axis. So as you can see, the effect of the equation of time is about plus or minus 15 minutes throughout the year. So if you look at a sundial and you look at your watch and you say, obviously the sundial's wrong, well, you probably haven't applied the correction of time yet. There was a change in time priorities from the idea that the watches, when they were first introduced, were not reliable and not accurate. So the sun was constant, and the time told by the sun was constant, and it was obviously the watches that were wrong. Well, watches and clocks got better, and suddenly it was realized that really what's changing is the effect of the equation of time on how the sundial displays time. Another effect is introduced by the fact that we have time zones. Now, time zones are strictly geopolitical. The orbit of our planet around the sun really knows nothing about time zones, and neither do sundials. But of course, if we look at our watch, it's important to us that we understand what time zone we're in. There are 4 time zones in the United States. If you happen to be in China, you're in one large time zone. So each one of these time zones is 15 degrees of longitude. Here, that's the typical time zone. Some individual countries are able to change that, and China chose to do so. Well, that introduces the cause for the second correction that needs to be made to reading sundials. Where are you located within your particular time zone? Remember that within that 15-degree wide longitude area, time is told by your watch remains the same, but time is told by the sun does not. So at a given location within that 15 degrees, there's a correction that must be applied to the time that's displayed by the gnomon shadow. And that's often done by rotating the position of the hour lines away from the nominal position on the midline of the sundial. And if you look here, you'll see that there's a little gap here, and in fact that gap is equal to the 14.6 minutes for this dial that was built for Devon, England. So again, there are 2 corrections that if you walk up to a sundial you want to make to understand what time in hours that we know would read on that dial. The effect of the equation of time, and there's usually an analemma provided on sundials to make that correction, and then either the builder of the sundial has included the longitude correction, in which case you don't need to include it or add it, or he has not, in which case you do. If you apply both of those corrections, and if the sundial is well corrected and well installed, it will be accurate. How did the math of sundialing evolve? Well, it's really spherical trigonometry. And I don't propose to give you a lecture tonight on spherical trigonometry, but I thought I would show you at least how some of the dial equations are developed. This is a plexiglass model that is not actually a sundial, but rather it's a model that shows the 4 geometric planes of interest in creating the math for sundialing. I have this device, which is a solar tetrad, again for you to look at on the display table. Each one of the surfaces here that lies in a plane has a triangle drawn on it, and you can see that triangles in adjacent planes or intersecting planes have common sides. That allows us to write equations for those 2 different triangles in different planes, but to relate the equations. Here are the 4 planes involved. Again, there's a horizontal plane, there's a vertical north-south plane, there's an equatorial plane, and there's a vertical east-west plane. And again, on this, you can see the sundial or the triangles drawn on each one of these planes, and recognize that this edge of this triangle and that edge of this triangle can be equated. You can write those individual equations here, and then the next step, if you remember from your high school trigonometry, is simply to divide one equation by another. If you follow that out, you come up with this solid trigonometry or spherical trigonometry equation, which is the basic equation used for calculating all sundials. Now, you can do that with a hand calculator, you can do it with some trigonometry tables, but the fact is there's very convenient software available today to do that. So if you have an interest in designing your own sundial, there's ample software and very user-friendly software available to do that. Let's talk about some examples of modern sundials, and we'll try again to look at examples of each one of the types that we discussed previously. We talked about Stonehenge. Of course, that dates from 1900 BCE, but people still make calendrical dials. And this is an example that was built in the summer of 2000, and it's actually built from growing corn. So naturally, it was called Cornhenge. But there are other calendrical dials that are recently built. Here is one in Tucson, Arizona. It's called Sun Circle Park. And if you look at these walls here, you'll see that there are openings in these walls. The alignments are such, this is a 50-foot diameter circle here, by the way. It was designed to celebrate the ceremonial life of the Anasazi culture. The Anasazi were sensitive to the seasonal changes, and there is evidence that some of their constructions were designed to identify the solstices. This dial is designed so that the rising sun casts a bright spot through these openings on the far wall, and there are actually inscriptions on these openings that will show the solstices and the equinoxes. Again, this is a very modern dial in Tucson. North American Sundial Society had its annual meeting in Tucson about 2 years ago, and when I took this picture. There are also very large sundials, and one of the reasons people build sundials today is as a memorial. In Kentucky, there is a Vietnam Veterans Memorial that was designed by Helm Roberts. Helm was at the North American Sundial Society meeting last year in Banff, Canada, and presented a very nice program on how he designed this particular sundial. This is a monumental size sundial. The dial is interesting in that it not only tells time, but Kentucky wanted something to recognize their Vietnam War dead. So the tip of the gnomon casts a shadow that falls on the engraved name of the fallen Vietnam veteran on the anniversary of his death. This is a very large dial. You can walk out on this dial face. And just as in the Vietnam Veterans Memorial in Washington, D.C., visitors to this dial come and leave mementos on the dial face. And as in Washington, there's a veterans organization that collects these and places them in a museum. Right here in California, this year in July, on July 4th, in fact, the folks up in Redding dedicated this sundial bridge. Now, this is actually a footbridge to a new public park in Redding. It was designed by Santiago Calatrava, who is a Spanish architect and extremely well-known bridge designer, has gorgeous bridges throughout the world. The objective Redding had was to have as open a space as possible around this bridge. They were trying to enforce the openness of this park. So they chose to have as little structure around the bridge itself as they could. So Calatrava's solution to that was to have a single pylon with suspension cables out to the bridge. The bridge, this is nearly the full length of the bridge. There is no corresponding pylon over here. The bridge is about 700 feet long. This tower is 217 feet high at this point. The park is actually over in here. And it just happens that the plane of this pylon is pointed at is aligned to north. Unfortunately, this angle is not exactly right. It's a little too steep an angle to be a true celestial north, so there are some corrections and errors that will inevitably result in the use of this pylon as a bridge, but as a sundial. Nevertheless, Reading identifies this bridge and advertises it and promotes it as the Sundial Bridge. The other interesting aspect is that the walkway on the bridge is glass. Again, that's in keeping with the idea that they wanted the bridge to be as open as possible. Examples of modern horizontal dials. These are typical dials that you would see in gardens. Here are two small dials that would be in a garden. Here is a larger monumental sized dial, and you can walk up these steps, and the hour lines are along here. But again, this angle would correspond to the local latitude, just as this one. Here is a modern horizontal sundial made in stone by one of the NASS members who lives in Tucson. In this case, the gnomon is actually it's barely visible, is a taut wire right here, and it's held taut by over this pulley by this hanging weight here, which is a spherical stone. Here is the shadow cast by that gnomon. Dials work up north too. Here's a dial that's in Helsinki. It's at 60 degrees north, and it might be interesting to note that the hours are shown all the way from 4 a.m. to 9 o'clock at night. And why is that? Well, that's because the sun actually shines there over those hours. And again, you can appreciate the 60 degrees here, the very steep gnomon angle. There is an even farther north dial. This is at Longyearbyen in Svalbard, Norway. This dial was just recently installed by a personal friend of mine who did the design and construction of this dial. There are polar bears up there, so he chose to produce the gnomon with the image of a polar bear. But again, you can see this very steep gnomon angle. This is actually at 78 degrees from the North Pole. Now at that location, the sun shines only 7 months of the year. So for 5 months, this dial doesn't work. But on the other hand, at the time it does work, for part of that 7 months, it shines 24 hours a day. The sun never sets. So if you look at the dial face, you will see that there are hours engraved completely around the perimeter of this dial. There are also dials for the southern hemisphere, but they look a little bit different. This is the same image that I showed you before with the latitude angle here with the gnomon pointed to the north celestial pole. Here is a corresponding figure for a horizontal sundial in the southern hemisphere. In this case, the gnomon in the upward direction points to the south celestial pole, but still points to the north celestial pole down here. It just happens to be below ground level. The other interesting item, of course, is that these hour lines run clockwise, but in the southern hemisphere, they run counterclockwise. Here's a picture of an actual southern hemisphere dial that's located in Melbourne. So this gnomon, or this style here, again, in this direction is celestial south, and down here would be celestial north. Let's look at some vertical dials. These are dials that are on the vertical walls of churches. These dials happen to be on walls that were built facing exactly due south, and that's a rather interesting characteristic. In that case, this gnomon hangs straight down. Again, at this angle, this gnomon angle pointing up here would go up to celestial north, but it's directly below the 12 o'clock line, or directly above the 12 o'clock line on this dial, because the dial is on a true south-facing wall. If the wall doesn't happen to be exactly south, and they didn't always build churches with south-facing dials, then the dial is said to decline. So a declining dial is one that's on a wall that is not exactly facing due south. You can tell this by looking at these dials by the fact that this foot for the gnomon is not exactly on the 12 o'clock hour line. and the same thing over here, it's offset. And that's to correct for the angle at which the wall was actually built. Sundials can also be built in churches with stained glass, and here's a very famous example of a dial in Basel, Switzerland that dates from 1731. You can tell by the irregularity of the hours that this is not on an exact south-facing wall. The gnomon for this dial is on the outside of the building, so it casts the shadow on the dial face, and the time is then read from the interior of the church. Here is a modern stained glass sundial, again built by my friend in Tucson. And you can look at the edge of this dial here and you can see the gnomon on the outside. So the idea is that the gnomon casts a shadow. There is a shadow from that gnomon. And the time is read from the inside. He actually has this dial installed in his home in Tucson. Well, here's a vertical wall dial that's also in Tucson. This happens to be on a bank building. Well, it is a due south facing dial, or nearly due south, because you can see that the gnomon is nearly in line with the 12 o'clock time. And I was able to, of course, in Tucson, get a nice shadow from that dial. Here's yet another vertical dial. This is in Calgary, Canada. Last year we had our North American Sundial Society meeting in Banff, and we toured Roger Bailey's home. And he has constructed this dial, and you can see that it has analemma correction built into it, and the gnomon is right here casting this shadow here. Well, what happens if you have an interesting surface that you'd like to put a dial on, but it doesn't happen to face south or north, and it also doesn't happen to be vertical? Well, an example of that might be a sundial dish or a satellite dish. And if you think of the satellite dish, it's kind of facing south, but it doesn't exactly point due south, and it's often rotated off to one direction. And furthermore, it's not vertical. So you've got to deal with the issue of the dial declining, that would be moving in this direction, east and west, and also reclining, that would be moving in this direction. Both of those corrections can be built into a sundial, and in fact, that's what was done here. There was a surface put on the on the face of this satellite dish, and in fact, it makes a very effective sundial. The math for this is a little more complex. You've got to account for the declination and the reclination of the dial. But again, the equation is a little bit more complicated than I showed you before, but with a handy pocket calculator or any of the sundial programs, you can do this math very readily. Here is a good example of a planar equatorial dial. Now, by planar, I mean that the dial face is flat. And as an equatorial dial, this face is in the plane of the equator. Well, the interesting thing about that is that the sun passes through the equator at the equinoxes. So as the sun passes into the other portion of the sky, you have to read this dial on its opposite face. So equatorial dials have hour lines engraved on both faces of the dial. The gnomon runs continuously through the dial. Again, it's aligned with true celestial north. But on the back side of the dial, it sort of points down. True celestial north would be up here, and the time is read down here. So as you pass through the equinox, you move from face to face on an equatorial dial. These are also called equatorial dials. I've never really convinced myself I understand why, but they're not planar equatorial. This dial, or actually it's this face that's in the plane of the equator. It really doesn't have much to do with the sundial. I would call this a polar dial, but with a curved face. Unfortunately, traditionally this is called an equatorial dial also. Now the fact that this dial face is curved, and in fact it's circular, allows these hour lines to be uniformly spaced. The gnomon here is a taunt wire, and there is an analemma drawn to provide correction for the equation of time. Here's yet another one of those dials. This supporting structure works as a horizontal sundial, and the hour lines down here for that part of the dial. This taunt rod is the gnomon for the equatorial dial. There are also armillary spheres. Well, an armillary sphere is nothing more than an equatorial sundial with confusing features added. features that don't benefit the sundial at all, but are interesting to look at. For example, if you look at this dial, you will see a ring that's in the equatorial plane, so the hour lines are inscribed down here. This ring is the Tropic of Capricorn, and this ring is the Tropic of Cancer. Well, they don't add anything except spurious shadows to the dial, but you do often see armillary spheres. Now here is an equatorial dial. This is local in Claremont, just northeast of here. This actually has a built-in equation of time correction that's accomplished by shaping the analemma, or shaping the gnomon in the shape of an analemma, so that the shadow that this gnomon casts is in fact a curve. And the graphic here on the edge face of the dial tells what edge of the gnomon to read for the calendar date. January, February, March, April, and unfortunately this dial has lost some of its inset letters. But using this analemma graphic tells you which edge of this shadow to read. So I took this picture in July, and we'll be reading this edge right here. So this thickness and this changing shape actually builds in the equation of time correction to this dial. As the seasons change, this shadow moves up and down along this path. Here's another type of equatorial dial with the equation of time correction built in, with an analemmic gnomon. This has a dual-purpose gnomon. This is a tabletop dial. Again, it has a circular dial face, so the hour lines are equally spaced. The gnomon can be rotated, and the gnomon can be slid up and down this axis. If the gnomon is in this position, then the sun, back over in this direction, casts two shadows, one from each edge of this gnomon. And you'll notice that there's a gap in the middle. So there are two shadows down here. The time is red in the gap between the two shadows. But you can also take this gnomon and turn it in such a way that the analemma-shaped hole in the face of the gnomon is what casts the shadow. And then you slide this gnomon up and down. There are date lines engraved on here. You slide the gnomon up and down so that the analemma is in the correct position for the calendar date, and you read the time from the inside edge with the analemma shape. So there are ways to build in the correction for the equation of time. In any of these dials, if you know where they're going to be located, you can change the hour lines to build the correction for the longitude or time zone. There are also sundials for the blind. Here's an example of one of those dials in France. The dial is unusual in that it actually consists of a glass sphere which functions as a lens to focus the image of the solar disk on these steel bars behind that lens. So the solar disk image falls on a bar, and the energy from the sun warms the bar. The blind individual can come up and with his hands determine which bar is hot, and braille numbers are engraved so that he can tell the time from a sundial even though he's blind. Kate Pond is a very well-known sculptor. She's also collaborated with some of the North American Sundial Society members to build sculptural sundials. This is a maquette, that is a model of a full-size dial that Kate built. The actual dial itself is big enough to climb into. This is, the size of a large bread box. It's about a 12-inch diameter pipe. There are two styles, and the two styles depict the appropriate edge for daylight savings time or standard time. So the edge, this edge or this edge here, casts the shadow, and you can see the hour lines are actually weldments on the inside of this steel pipe. In Belgium, there's a public park called the Sundial Park, and in this park there are many, many examples of different kinds of sundials. I have a picture of a few of them. This is really a calendrical dial. These two pillars have a gap between them, and there is actually near the top here a little bar that joins them. The slit passes a beam of sunlight which falls onto these tiles when the sun is due south, or local noon. Here's a polyhedron dial. Each face of this dial, here's a vertical dial face. Here's an equatorial dial face. There's another vertical dial face over here. So it's possible to build, with different kinds of gnomons, it's possible to build dials on each one of these faces. We saw some historical examples of a polyhedron dial. Here's a modern example. Here is a polar dial. Now, we haven't seen a picture of a polar dial before. Here is a very good example. This is made in stone by, again, my friend in Tucson. The surface is flat. The gnomon is a plate, the top edge of which is precisely aligned to celestial north in this direction. And the style is the top edge of that plate, which casts this shadow here. So the time is read from this shadow. Now, since this is a planar surface, not a curved surface, then the hour lines are not equally spaced. And you can imagine that as the sun drops lower and lower in the sky, the edge of the gnomon, the shadow here, moves more quickly, and therefore the hour lines are farther spaced. Sometimes you'll see these dials with the ends turned up, and hour lines wrap around that joint so that you can read them later in the day. Here's another dial in Belgium. Again, this tells both the date from this notice here, and these are date lines, and they're shown with the astrology symbols here, or time with this shadow by these hour lines. There are also pocket sundials, and here are two examples of historical dials. This is an ivory dial. It's a very beautiful thing. Here's one that is made in brass. This one dates from 1574. This one's a little later, about 1602. This is a compendium. That means that it has different kinds of instruments built in, including the sundial, or different types of sundials. Here's a modern analemmatic dial. Now remember, we talked about the analemmatic dial functioning by an individual standing at a fixed position on the face of the dial. So here is a set of dates. This would correspond to the analemma dates. And the individual walks into this dial, finds the appropriate current date, and stands on that stone. And then the vertical body and head of the individual would cast a shadow on these posts to indicate the time. This is in Calgary, Canada, in a very nice scenic park there. So this is kind of a participatory sundial. It's not unlike being able to walk out on a dial itself. In this case, you not only walk out on the dial, but you actually form the gnomon as your body. Here's another analemmatic dial. This is in Tucson. There's a large analemma here, although the analemma itself isn't important to the functioning of this dial. What is important are these dates alongside the analemma. This is outside the Flandreau Planetarium in Tucson, and because of the visitors they have there, they felt compelled to explain that this exhibit only works when the sun is shining. Here's an analemmatic dial that was built by some elementary school children and painted on their concrete playground surface outside the school. This is in Calgary again. This lady is actually the spouse of one of our North American Sundial Society members when we were at the Banff conference. And she is standing on the date mark that corresponds to the current date. So it could be anywhere from here to here. So the position of the gnomon moves during the year to correct for the equation of time. I promised you sundials from prehistory to the digital age. Here is a digital sundial. This one actually is in that park in Belgium again, and it displays digital numbers that are accurate time, and that's accomplished by having slits in different surfaces that the sun shines through. Interestingly, though, it's important that this point to true celestial north. Well, sundials work other places too. How about Mars? This is the sundial that's on the Spirit and Opportunity rovers on Mars. This dial has some interesting history. This device was originally placed or designed to be placed on the rovers for use with the stereoscopic camera. And it provided color correction chips and grayscale and a nodus up here, that's N-O-D-U-S, nodus, that was to cast a shadow. And you can see the shadow of that nodus down here on the surface. Well, those were required to calibrate that stereoscopic camera on the rovers. Bill Nye, the science guy, walking through NASA JPL, saw this and said, that's a sundial. And he was able to convince NASA to modify the device slightly so that it could be used as a dial after it landed on Mars. The problem, of course, is that once the rovers land on Mars and they drive around, you don't know what direction they're facing. So the orientation of this dial is going to be continuously changing. But we took care of that with a computer program. And in fact, up here in this inset picture, you can see hour lines that have been projected on this dial face by a computer program here on Earth. And upon landing of the first rover on Mars, JPL had invited school science teams, 2 individuals per week for a period of about 6 months, to come to JPL, participate with the science team there, and their job, among others, was to every day take the picture from the camera on the rover, run it through the software at JPL, project these hour lines for that sundial, and post it on a website. There are other devices that use the sun. This is a diplatoscope. This device was used extensively in England to set the railroad station clocks. And that was done right up until about the 1920s or so. It has a compass. It has various angles inscribed here. You set these up for the location that you know you're at. There's a prism in here, and you look through this little telescope at the images of the sun on that prism. And the 2 images come together as the sun is directly overhead. So when the sun is precisely vertical, it is precisely local noon. And then knowing the location, that was correctable for the time of day. This is how the British railroad station clocks were set for many, many years. This isn't really a sundial, but this is a device that was used during World War II. It's called a sun compass. They had a problem in North Africa. They had these big steel tanks out in the middle of the desert. The tanks were magnetized because there was so much steel in them, and therefore magnetic compasses just didn't work inside the tank. Plus, the tanks were kind of rough driving across the desert, so they couldn't tell the direction from any kind of compass at that time. Well, they used a solar compass or a sun compass, and this is a device that was actually built here in Los Angeles by a company that is still in business but not building sun compasses. It was placed in the tank or Jeep, and again, you can see the equation of time corrections in here. The sliding bar is set for the current date. The vertical gnomon casts the shadow, and by rotating this, they were able to determine where true north was for the particular time of day, and they actually navigated the tanks using this device. I've talked several times about the North American Sundial Society. I wanted to show you some of the things that the members do. While we were in Banff last year, we visited a park in Calgary, and in this park there had been a sundial. Unfortunately, the sundial had been vandalized. It was on this pedestal, and this sundial had been completely vandalized. Roger Bailey, who is this gentleman here, designed and built a replacement dial for this pedestal, and while we were in Banff, or in Calgary last year, we unveiled the replacement dial, which was a contribution from NISS to the city of Calgary. This is Fred Sawyer, who's the president of the North American Sundial Society. Well, you should recognize this. This is the Kitt Peak McMath Pierce Solar Telescope. There is a heliostat mirror up here that tracks the sun and shines an image of the sun down this tower. And the solar telescope working parts are actually down here below ground level. Well, for that heliostat to work, this path must be along true celestial north. So this building structure has edges that are aligned to true celestial north, just happenstance by virtue of the design of the telescope. One of our members, the member who designed those very nice stone sundials that we saw earlier, went to the astronomers at Kitt Peak and suggested that he develop the math and place markers on the ground around this telescope so that the stiles or edges of the tower could be used to tell time. And in fact, here's a picture. Here's one of the engraved markers placed on the, this is really just a pebble surface around the telescope. This is a shadow sharpener. It's a disc or flat plate with a hole punched in it, and placed at the appropriate distance. It's actually used to sharpen the image of the shadow, so you can read it with higher resolution. Paul Nibley is a member and built these two noon cannon. Now, again, this is not really a sundial. This one has a reflector, a mirror reflector. This one has a lens up here, and they're arranged so that when the image of the sun at a particular time during the day falls on the focal axis of that optical device, it focuses the solar image on something part of this dial and tells the time. In this case, there's a firecracker that's placed in here, and the solar image actually lights the firecracker fuse. In this case, the solar image burns a string. The string is used to hold these two brass pedals together, which are in the shape of a butterfly. So when the appropriate hour arrives, it burns the string, the butterfly's wings fall out, and you know what time it is. Well, sundials have been at the leading edge of astronomy and precision instrument making for many centuries. I believe the dials still have a part to play in our current usage. And if you remember the dial for the Kentucky Vietnam Veterans Memorial, they also make good focal points for buildings and public parks and memorials. This slide has a listing of sundial societies, and you can see that here there are 1, 2, 3, 4, 5, 6 sundial societies that I'm showing. Different kinds of sundial software that's available. Commercial sundial suppliers who will custom design a sundial for your location, an accurate sundial for your location. Don't believe if you walk into your local garden center or order from Wind and Weather that you're going to have a sundial that's accurate in your own backyard. But one can be designed and can be constructed, and with this software here, you can do it yourself. And then here's a list of notable sundial related websites. Now this slide I have reproduced, and it's available as a pass out on the display table down here. And there you have it. Do we have any questions?